In this section, we're going to cover power functions. So the definition of a power function is a function in the form of f of x equals kx to the n, where k and the power n are non-zero constants. And they give you some examples here: 17x to the fourth, negative 6x to the 1/2, 2 over 3x squared. These are types of power functions. Now, this is different than an exponential function. An exponential function we will cover, but in those, the exponent is our variable. So those are different than power functions. Power functions, the exponent is a constant, where our variable is in the base portion here. So here's some examples of some power functions. We're very familiar with something like this, x squared. This is a quadratic. And then we have x cubed, which does this little slope. You can see both of these are continuous functions. And what you find is that you can start predicting how these functions are going to behave on the end by those exponents. And so when we look at end behavior, we notice that this x squared had the ends of the graph going the same direction. And in fact, they were both going to positive infinity. Whereas when we had the x cubed, you'll notice that the ends of the graphs went different directions, one going down, one going up. And you will see that pattern repeat as you look at these exponents. So I like to make a little chart to remember this by. When you have a function, you are going to look at the degree. So, for example, if we had this x squared, and even if we had a 3 in front of it, that degree is even. And so anytime your degree is even, your ends of the graph are going to go the same direction. And so in this case, we're going to look at the even graph. And the second thing we're going to look at is the leading coefficient, so the number in front of that variable. Those two things will tell you how this particular function is going to perform at the end. And so if the degree is even, the ends are going to go the same direction. And then to determine how the direction they're going to go is we're going to look at this leading coefficient. If the leading coefficient is positive, it is going to go up. And if the leading coefficient is negative, it's going to go down. So for this graph 3x squared, the endpoints are both going to go up. And so how we're going to write that using our limit is the limit as x goes to the left, or negative infinity, so as x goes to the left, well, that limit is going to go up, positive infinity. And the limit as x goes to the right, or to positive infinity, is also going to go up. Now that changes when you have a leading coefficient that is negative. So if that had been a negative 3x squared, both of those ends would have gone down. So it would have looked something like this. And now we see that the limit, or what y is doing, as x goes to the left is negative infinity there, well, y is going down. So we're going to say, well, that's negative infinity. And then the limit as x goes to the right, well, it's also going down. So that is also negative infinity. So that's if your degree is even. Now, what happens then if your degree is odd? Well, if your degree is odd, they go different directions. And once again, we're going to look at that leading coefficient. So let's say we have 3x cubed now. In this situation, 3x cubed means that my endpoints are going to be going different directions. But just like the degree being even, it is still going to be going up. So if you were to draw a graph that continuously goes up, it looks like this. Well, as we look at this in limit form, as x goes to the left side of that graph, so as x is going this direction, my y is going down. So we're going to say negative infinity. And as my x is going to the right, or to the positive direction, my y is going up. And then you can probably guess what happens over here if I have an odd degree and my leading coefficient is negative. They're still going to go different directions, but it's going to go down. So on the left-hand side, we actually start up and we go down. So if I were to do this in limit theory, I would say, well, as we look at x going to the left side, meaning as we look this direction, my y value is going up. But as we look that x is going to the positive direction, my y is going down. And so that is what you can tell from that degree. You can tell the end behavior of your functions here. So we would say when we look at something like this that it is increasing on the interval, and it's pretty, there's a lot of words here to explain it, but basically your graph is going up if it's increasing on an interval. This just means that as x gets bigger, y gets bigger. And from the same point, it's decreasing if as x gets bigger, y gets smaller. Visually, it's very easy to see. And then constant, as you can see, again, visually very easy. As x is getting bigger, y doesn't change at all. This is constant here. And so those are the things that your x can do over different intervals. So then let's talk about an even function. Now this is a little bit different. Yes, you're going to look at your degree, but at the same time, other things have to be in place. In an even function, you should be able to plug in a positive and a negative of the same number and get the same number. So if I plug in a 3 to x squared, I get 9. If I plug in a negative 3 to x squared, I get 9. This is considered an even function. For an odd function, it is considered odd when I plug in a negative and positive of the same number and I get a negative and positive of the same number. So in this example, if I plug a 4 into this x cubed, I get 64. If I plug in negative 4, I get negative 64. That's how you know if a function is even or odd. So let's look at this particular function. We're going to talk about end behavior, and we're going to talk about even and odd. When you don't have any addition and subtraction, it's just a direct variation. And then you can see quickly that this is an odd function. If I were to plug in a negative 1, I would get negative 1 to the 5th is negative 1. I'm going to get negative 1/4. If I plug in a positive 1, I'm going to get positive 1/4. Clearly, this is an odd function. And then let's talk about end behavior. So if I look at end behavior, my degree is odd. They're going to go different directions. And my coefficient is positive. It's going to go continually up. And so if I look at this graph, yep, it goes continually up, which you can see. And if I did it in limit theory, it's going to look just like the other one. It's a little jumbled there, but you can see as x goes to the left-hand side, my y goes down. As x goes to the right-hand side, my y goes up. And that's what we're looking for when we talk about end behavior. So take a minute and try this and see if you can figure out the end behavior of this function, what this would look like. Hopefully you were able to notice that this is an even number, which means they're going to go the same direction. And then we're going to look over here, negative in front, they're going to go down. Both of these are going to go down. And so this function is going to go down on both sides, meaning as x goes left, it goes down. As x goes right, y goes down. Now, a little more familiar topic is direct variation. Direct variation is when you have a function that y is directly related to x being multiplied by some constant. You do not have a plus or minus here. It is directly varied by this x and a constant. And circumference, 2 pi r. That is a great example of direct variation. Circumference is directly related to that radius, multiplying it by 2 pi. That is a direct variation problem. You can also have direct variation with powers. Again, no plus or minus, but you do have x to a power. Area is a great one, pi r squared. Area is directly related to the square of the radius, and that is a direct variation with a power. So let's look at these examples. When an object is traveling at a constant speed, the distance traveled varies directly with the elapsed time. And so we see that word directly, varies directly. So that's really important here. Varies directly. with the elapsed time. So we have these variables that we don't know. We don't know distance. We're going to say distance here is D. And then varies directly with time. So we're going to say, well, time is going to be that T. All right. And as we look at this, we want to set up what we know. So we're going to say distance varies directly. Well, that means some constant times t. And then they've given us some information. If it took 2 hours to travel 50 miles, find the distance traveled in 7 hours. All right, 2 hours to travel 50 miles. So 50 miles was our distance. 2 hours was our time. That constant will always be this left variable over here divided by this right variable here, all right, which in this case was 2. So our k here is 25. And now we can solve for anything they give us. We're going to say, well, the distance is going to be 25 times the time. So if we want to know how far they traveled in 7 hours, well, we're just going to plug that 7 in. The distance is going to be 25 times 7, which is 175 miles. Now you can also have direct variation with a power function that is positive, or an inverse variation, meaning the power function is negative. Inverse variation here is another way that you can vary with a function. And so for inverse variation, they're going to say some variable varies inversely with some other variable, and in this case, variable squared. So for this example, it says the illumination of an object is inversely proportional. That tells us we have an inverse variation to the square of the distance. So we have I is inversely proportional to the square of the distance. What is the illumination of the object? 6 meters from a lamp. If the illumination 2 meters from the lamp is 150 lumen. So they've given us the illumination. We know that that is when the object is 2 meters. So we are going to plug in that 2 meters, and we are going to square that, and then we're going to solve. So we have 150 times 4. 150 equals k over 4. Multiply both sides. That k is 600. Well, if we want to now find out the 6, we're just going to write our equation. We're going to say, well, our equation is L equals, now we know what k is, 600 over d squared, and we can find it for any distance. The distance they now want is, what is the illumination for 6? Well, plug it in. L equals 600 over 6 squared. And when you take that to one decimal place, you should get approximately 16.7 lumen per meters squared. So obviously you can't solve this one, but go ahead and try setting this up and see if you understand the concept of taking this word problem and setting it up with a variation.